Welcome back after the break. Obviously, we've been discussing global air circulation. And just before the break, we have established the movement of air. Vertical movement of air, if the air rises, to low pressure. When the air sinks, it's known as a high pressure. The movement of air horizontally is known as wind, and wind moves from a high pressure to a low pressure. Now, to explain the global air circulation, I'm going to draw my own diagram with that set of information over there in my own diagram. Now, we have already established, let me just quickly wipe this out. Simple reason why is that I struggle to see the black. So let's just use nice colors, bright colors. Okay. So obviously, right here, center bang in the middle, we have the equator. Then we have the 30-degree latitude line. That's where we actually are, South Africa. We are dominated by a high pressure belt. Then we got the subtropical, subpolar low pressure belt. And then we got the polar regions. Now, Gr12 we already established, right? The reason why the equator experiences much warmer conditions is because of the insulation that it receives. The distance that the insulation travels is much shorter over there than over there. And in fact, if I walk towards the equator, what's going to happen with the temperatures? It's going to increase. If I walk towards the polar regions, what's going to happen with the temperature? It's going to decrease because of less insulation. Now, very importantly over here, the type of pressure that we experience at the equator is a low pressure. Why is it a low pressure? Because it's warm tropical climates. It's warm temperatures every single day. Believe it or not, the equatorial regions don't actually experience winter. Why? Because of the amount of insulation it receives every single day. Now, I'm going to jump straight from the equator to our polar regions. And if you look at the polar regions, like the South Pole, what do we know? We experience very cold temperatures. If you look on the TV, it's usually covered with ice and snow. Now, what type of pressure do we associate cold temperatures with? A high pressure. So am I right when I'm saying that the polar regions experience a high pressure? So this whole 90-degree latitude line is dominated by a high pressure belt. Now, if you look at the equator, it's rising air because of warm conditions. What do we know? It's a low pressure. Now, for argument's sake, if I go and climb Kilimanjaro, I'm standing right here and I go and climb Kilimanjaro, what's going to happen with the temperature? In altitude, what happens with temperature and altitude? Temperature decreases. Now, as this air rises at the equatorial regions, what happens? It rises, it cools, condenses, cloud formation takes place. So it rains. But in Gr10, you've learned about the structure of the atmosphere. We experience divergence of air in the upper atmosphere. Divergence is when something moves away from one another. Convergence, when something moves towards one another. In Gr10, you've learned about moving plates. If something comes together, it's convergence. When something moves away from one another, it's divergence. Now, as the air diverges in the upper atmosphere, eventually what will happen? It will cool down again. Now, like I've mentioned, if I'm climbing Kilimanjaro and I go up in altitude, what's happening with the temperature is decreasing. Now, at the 30-degree latitude, because of the divergence taking place right over here, the air starts to sink. Right? Because it's moving from a higher altitude to a lower altitude. Now, as the air comes to the surface, what happens? The air can't go right through the surface, am I right? So, once again, as you can see, the air can't go straight through the surface. What's happening with it? Divergence taking place. Now, with all this rising air at the equatorial regions, it's leaving a void. So what happens? With the divergence taking place at the 30-degree latitude line, it's getting sucked up here at the equatorial regions. And when air comes together, it's known as convergence. And what do we call this area between 0 and 5 degrees? The ITCZ, Intertropical Convergence Zone. The name basically gives the way. Intertropical, this is tropical regions all around the equator. Air is converging over here because it's coming from the high pressure systems over there. Now the air rises. Now keep in mind there's a void being left. So the air is getting sucked in from the subtropical high pressure systems over here. Now, as the air diverges at the 30-degree latitude line, what happens? Let's move back to the polar regions quickly. Obviously, what do we know? It's a high pressure system because it's sinking air. It can't go through the surface, so divergence takes place. Now, please pay special attention to the 60-degree latitude. There's divergence taking place over there and divergence taking place over here. Now, what happens over here, Gr12? Convergence. But look what happens over here. From the one side, we have cold air coming in. From the other side, we have warm air coming in. So, what do we know by now? If warm air and cold air have to collide, what's the cold air going to do with the warm air? It's going to force it upwards. So what's being created over here? A low pressure. Not because of warm conditions like at the equatorial regions, but because the air is being forced to rise because it's where there's convergence of cold air and warm air. Now, what basically develops over here? We got rising air at the equatorial region, so that's the equatorial low pressure belt that developed over there. Now, where the air sinks at the 30-degree latitude line, that's a high pressure belt. And at the 60-degree latitude, where there's cold polar air and warm subtropical air coming and gliding, convergence of air, the warm air is being forced to rise, we experience a subpolar low pressure belt. Now, like we've mentioned in the beginning of this episode, a low pressure system is rising air because of warm conditions. So obviously the equatorial region, we can tick that box. Or it's rising air because the air is being forced to rise, as you can see from this warm subtropical air and cold polar air converging to one another. And then obviously high pressure systems over there, as you can see, it's sinking air because of very cold conditions, and as you can see, the high pressure system over here develops because of divergence in the upper atmosphere and sinking air over the 30-degree latitude. Now, very importantly, let's not forget the movement of this low pressure and high pressure systems in the southern hemisphere. Anti-clockwise, clockwise, anti-clockwise. Okay. Now, that's the vertical movement of air. Now, with this vertical movement of air, we got three distinct cells that formed. The polar cell, the Ferrel cell, and Hadley cell. Let's just quickly go back to our information on top of the page. There you got your polar cell, your ferrule cell, and your Hadley cell. As you can see, the warm air rising, cold air sinking. Okay, divergence taking place, sinking, sinking. Right, so our three distinct pressure cells have developed, the polar, ferrule, and Hadley. Now, the next thing I want to explain to you, we've looked at the vertical circulation of air, vertical movement of air. Now let's just quickly look at the horizontal movement of air. Now very importantly, I've explained to you that air moves from a high pressure to a low pressure. So in theory, air moves from there in a straight line to there, in a straight line to there, from the high pressure to low pressure. But unfortunately, it doesn't. Now in grade 11, you've learned about Coriolis force. Now what is Coriolis force? It's the deflection of the winds by the Earth's rotation around its own axis. Now the simple rule of thumb is, if you stand with your wind against the back in the southern hemisphere, the wind will deflect to your left. When you stand with your back to the wind in the northern hemisphere, the wind will deflect to your right. Now, let's say for argument's sake the air blows from the high pressure to the low pressure, and we are in the southern hemisphere. Which is the wind going to deflect to? To your left. Now let's just quickly go back to our diagram over here. Because of Coriolis force, the air doesn't move in a straight line from the high pressure to the low pressure. So what happens? It deflects to the left, right? Wind is named from direction it's coming from. North, east, south, west, right? So what do we call these winds? The polar easterlies. As you can see, we got the polar easterlies over here. Now, the air moves from a high pressure to a low pressure, but because of Coriolis force, it's deflected to the left. What did we experience over there? The westerlies, and air moves from a high pressure to a low pressure, but in the southern hemisphere, deflects to the left. And we got tropical easterlies. If we quickly look at the next page, because of the deflection, we got a tropical easterlies. Why the tropical easterlies? Because it's very close to the equator. If we look at the polar easterlies, why the polar easterlies? Because it's very close to the polar areas, 90-degree latitude line. And if you look at the westerlies, it's basically in your mid-latitudes. Now, let's just quickly go back to our top diagram over here. There you can see it. There's your subpolar low pressure. There's your high pressure. There's your low pressure, high pressure, low pressure. Okay? Keep in mind that deflection is different in the northern hemisphere. So let's look at the southern hemisphere. High pressure, low pressure, high pressure, low pressure. Because of Coriolis force, deflected to the left. Because of the Coriolis force, deflected to the left. Because of the Coriolis force, deflected to the left. And as you can see, tropical easterlies, the westerlies, and the polar easterlies. Now, so in this lesson, we've covered the following concepts. the synoptic charts. Most importantly over there, you need to be able to determine what season the synoptic chart is, how to read the synoptic chart, and how to interpret the synoptic chart. Keep in mind the little clues like the date, the temperature on the weather station models. Look at the Calaria high pressure system. If it's over the interior, what do we know? It's winter. If there's a low pressure over the interior, it's a summer because of very warm conditions. The temperature, cool temperatures, winter. Very warm temperatures, summer. And a dead giveaway is obviously our date. Then we look at the high pressure systems and low pressure systems. Once again, what do we know about high pressure systems? It's sinking air, anti-clockwise circulation. Okay, low pressure systems, it's rising air, clockwise circulation of air in the southern hemisphere. Remember, both of them for the southern hemisphere. And then the weather station models. Very importantly, grade 12. It's easy marks, describe the weather and use the symbols as being in the weather station models to be able to describe the weather. For instance, tell us what's the temperature, tell us what's the dew point temperature, tell us the cloud cover, tell us the wind direction and the wind speed. And finally, global air circulation. Global air circulation, we looked at it, the vertical movement of air and the horizontal movement of air. Now, as you know it, vertical movement of air is the low pressure systems and the high pressure systems, and the horizontal movement of air is air moving from a high pressure to a low pressure. But very importantly, unfortunately, air just don't move from that high pressure to the low pressure, because we got a force, and is known as the Coriolis force, that deflects the wind. Now this wind is deflected because of the rotation of the Earth around its own axis, and that deflection is to the left. And that creates the polar easterlies, the westerlies, and the tropical easterlies. Thank you for watching. Until the next time.